Diffusion models have revolutionized the generative AI field because of the amazing images that they can generate from a given text prompt. They have really democratized the generation of images so that anyone, just by typing few text prompts, they can generate the images. Here's an example of a Mid-Journey tool that I'm showing you up here. And if I type a simple prompt to the Mid-Journey, asking it to generate and how to embrace AI in the workplace. Yeah. So as you can see, it is generating the images for a prompt that I have specified here, and it really captures the meaning of the prompt. It is really showing the humans and robots working together, right? Now this works well for a general prompt where you don't have any specific information about a person or a company, right? That is how these models like Midjourney have been trained on a general purpose web data. There are also other tools like Dolly from OpenAI, as well as Firefly from Adobe, a Firefly tool from Adobe, which do similar things. Now, the challenge with these generative models are they cannot really generate the images that a company, a branding, or maybe an individual person, if he or she wants to incorporate their own images into the prompt, they cannot do that, right? Easily, out of the box, I mean. Like for instance here, let's say I work for an Acme company, and if I type a simple prompt where I'm saying the team collaboration in a modern office space, it just generates a very generic image that can signal really any company in general, right? But let's say I work for an Acme company which really specializes in merchandising clothes, then the image that I'm really looking for is something like this, where I could see like a lot of mannequins wearing the clothes that signifies the brand of my company, and also some of my company logos shown in the picture. But at the same time, it is really capturing the teamwork and collaboration also, right? In a similar manner, like a company wants to add the brand in the picture, an individual also wants to show his or her image in the picture itself, right? So that is not possible if you just use pre-trained model which are available in the open source space like Hugging Face. Out of the box, it's not available. So you need to be able to fine-tune these models so that the branding information and also the personal images can be considered in the prompt when we're generating the image, right? Now, as you know, this diffusion model, just like large language models, are very expensive in terms of storage and the compute requirement, right? So we need to find a way how to efficiently fine-tune this model. One of the way to do that is parameter efficient fine-tuning technique that can be used to really fine-tune this model on a custom data set, but at a very low cost, right? So this parameter efficient model have multiple advantages, like they are more efficient. We can do faster training with it. They are more flexible because we can support multiple versions, and they also can be used to reduce the overfitting in the model. So there are several techniques, PEF techniques that can be used to find the model, which includes using some adapters, prefix tuning, then the tuning of the prompt itself, and there's one more technique called low rank adaptation, which is what we will cover in this particular video. So what is LoRA? So LoRA stands for low rank adaptation. It's one of the technique under parameter efficient fine-tuning category to really fine-tune the model in a most efficient way. The intuition behind LoRA is typically large diffusion model or even large language models, when they are getting pre-trained on a general purpose web, they definitely require high rank metrics. Okay, but when you are fine-tuning these diffusion models on a on a smaller corpus, the weights of those diffusion model can be approximated by using a low rank matrices. Okay, that is the main idea behind this technique. So, well, what does it mean? So typically, the diffusion model have the millions and the billions of parameters, right? So in order to fine tune the weight matrix, if you look at that, it is really high. And when we are fine tuning, we are going to decompose. So we are going to freeze the matrix that the pre-trained model has, and we will generate a delta changes which has the data from the custom training data, but expose them as a low rank matrix, right? So what is a low rank matrix? A matrix is said to have a low rank when it can be represented by a decomposed matrix having a lower rank. So here take example of a matrix A, which is a 5 by 5 matrix. And if we can express that as a decomposition or a product of two matrices, like for example U and V, and let's say by multiplying these two matrices you can get the original matrix, that we say the matrix A has a rank of 2 because they can be decomposed and computed by the product of two other matrices which have a rank of 2, right? And that is the idea behind the LoRa technique, to decompose the weights, right? So typically in a diffusion model, when we are fine tuning, we are basically changing the weights of the model by certain amount called delta, right? So here the original, so here are the modified weights. W represents the weights of the original matrix, which we freeze, which we don't change, and we add the delta changes. Now these delta changes we express as a product of two low rank matrices, where the rank is some hyperparameter that we can pass to the model and control, right? So let's say let's say if the original matrix is the size of D by K, then this two matrix we can construct by decomposing into two matrices A and B, where where A is size of D and D by n R, and B is the size of R by K, right? So when we decompose the matrix, typically what happens is the storage size is not D by K, but it is D plus K into 2 into R, right? That's the idea. So here is the visually depiction of how the LoRa changes the game. So here is the without fine tuning. What happens is we have an input, we have a full matrix which has the billion parameters, and there are a number of such matrices for each layer, right? As you know, in the transformer layer that is there present inside the diffusion model, right? It is a very big model. So when we are fine tuning it, what we do is we keep this original model unchanged, but we introduce two low rank matrices, and then we add those weights to the original matrix, and we use the new weights for doing inference, right? So during training we compute these two low rank matrix and keep it as a different layer, okay? And then during the inference we just combine those weights with the original model, so that model learns the new concepts in the training data. So here's a typical saving example with the LoRa. Like a typical 175 billion GPT-3 model has about 12,288 by 12,288 inside each of its transformer blocks. That's a weight matrix. It's about 150 million parameters, and if you can successfully adopt and decompose that matrix into product of two matrices which has a rank of 8, then we just need 12,288 by into 2 matrix, right? And we just, the resultant parameter size is 197k instead of 150 million k, right? So that is the size of this matrix we're talking about, right? So that's much lower. So that's the reason the LoRa is very memory efficient, adaptable, highly composable, because since the LoRa layers can be kept separate, we can generate multiple such layers for each product customization or a person customization that we want to do, right? And it's reversible because this is an additive. If we don't want this, we can remove also. So the original models, we keep it separate and we don't impact the model, right? And typically the way it happens is these LoRa models are applied to the attention layer inside the unit model, which is a core model that learns to find the noise inside the image inside a diffusion model, right? So, so that's good. That's a theory about the LoRA model. Now let's start. Let's jump into the code. Let's look at some code. So I'm using Google Colab Pro for this particular exercise. Google Colab Pro is just available at this particular website, and you need to, because this exercise definitely need a GPU. So the cheapest way to get the GPU is to subscribe to the Colab Pro. So you need to go to this website called Colab Research google.com. If you're not member, just sign with your Google account and pay. I think this subscription starts at about $20, and if you really need dedicated GPU, you can do it for about $50 per month, right? So we need to also make sure that just create a new notebook by going to the file and just say a new notebook, and it will create a new notebook for you. And then we need to make sure that we select GPU for this exercise. So you go to the runtime, change runtime type, and make sure you select A100 GPU, which is the best GPU for this exercise. This GPU is from NVIDIA. Now we need to make sure that the environment really is selected GPU. So we can run this NVIDIA-SMI command to see the GPU is indeed installed. So we can see that A100 GPU is being used for this exercise, and it has also RAM of about 40 gig, which is good enough for this exercise. Then what we need to do, we need to install the diffuser library from Hugging Face, and we are just going to do this by cloning the diffuser library, because instead of installing, if you just clone it, we get all the latest changes that the diffuser library has. And we also install the prerequisite that diffuser library requires, and in specifically we are also going to focus on text to image, which is the diffusion model, and there are additional requirements which are in this file, and we are going to install that as well. So these are the prerequisites for our fine-tuning our diffusion model. So it's installing all the prerequisites for us. Okay, so it has installed a bunch of libraries for us. It is giving some of the warnings and just telling us the dependency involved does not take into account all the packages, and there are some dependency conflicts. I think but we can still live with these errors, right? We don't have to worry too much about it. So once all the dependencies are installed, the first thing I want to do is I want to check the performance, the quality of the diffusion model out of the box on a prompt that contains a person name which the diffusion model doesn't know about, right? So for example, I'm using a prompt called Ankush Chaudhary wearing basically a robot costume, and this Ankush Chaudhary is diffusion model doesn't know about it because this is not a very popular person which is available in the web data. So let's see how the model performs with this prompt. And I'm using a specific version of Stable Diffusion, which is a diffusion model from this company called Runway ML. Then I'm just instantiating this particular model by using the Hugging Face Stable Diffusion pipeline library. That's going to just load this model into the memory, and it is going to use the float 16, the accuracy of the data type it's going to use for that. We are going to convert the entire model to GPU, and then we are going to supply a prompt, and we get an image output. Really trying to generate an image from the pre-trained model for this prompt, where I have custom name of a person. Let's see how it looks like. So it really generates the image of a random robot. It really doesn't understand the concept Ankush Chaudhary that I have supplied to it. Let's try one more command, one more prompt after this, where I am saying Ankush Chaudhary running in the forest. Let's generate the image for it. And as you can see, it is really just generating the image of a random person, but not the Ankush Chowdhury. So if you really want to look at who Ankush Chowdhury person really is, then I'll show you. So this is the Ankush Chowdhury person. I really want our model to really understand it. And we basically need to fine tune. We need to generate the training data set with this image, give it to the model, fine tune it, and then see how the model performs once we fine tune the model. That's what we're going to do in next few minutes. So the first thing that we really want to do is to generate a training data set, right? So to generate training data set, here is the code. We're just going to first create a folder where we're going to download all the images and store it. And then we're going to label it. So what I've done is I've gone to the Google and downloaded all the images and specified the URL of the person. And there are some 24 URLs that I have carefully picked. And just by going to this URL, I'll give you a sample URL. You can go to the Google, search for this person and pick an image and then use that URL, put in the code, and then we will download the images, right? So I picked some 24 such images and I put into this list called URLs. Then I've written a code to download these images from the URL, and I'm going to resize it to 256 by 256. So this image will really get the image. Then we are going to download it. We are going to resize it, and we are going to save it inside this folder that we have created earlier, right? And we are going to do this for all the 24 images in the folder. Now, once we have images in the folder, what we are going to do is we are going to caption the images, right? We're going to caption the image, and we're going to use a blip model from Salesforce, which basically takes the image from a URL and it can generate the label for that particular image. So I'll show you first. Let's download the images and then caption it. So it's downloading the images, saving it. So it's downloading the images and it's giving this generating the caption. Basically, caption describes what the user is doing on in that particular image, and it's going to do this for all the 24 images. Now blip, when it generates the label, blip also doesn't know about Ankush Chowdhury. The blip is just going to give a label like a man, a person doing some activity, and then we are going to do some text processing where I am going to replace this a man with Ankush Chowdhury, a person with Ankush Chowdhury, and some of the things with Ankush Chowdhury, because I want to specify these labels or captions for this particular image set only, right? So I'm doing some post processing after blip caption generates the images. And then what I'm going to do is I'm going to upload this particular data set to Hugging Face. Okay, and to do that, basically we need to import a bunch of libraries from Hugging Face, because I don't want to do this again and again. Once I generate this data set, I just want to put it on the Hugging Face data set, so that next time I need it, I can just download it. So data set requires two arrays inside this dictionary. One is the image and the other one is the text inside the image, right? And the way I do that is I'm going to go through these arrays which have the URLs and the captions. Then I'm going to create this data set and I'm going to upload this data set to Hugging Face, right? This is the token I'm using. You can use your own token by going to Hugging Face here. I'll show you how to do that. So if you haven't created any account, go to the Hugging Face, create an account, then you go to the settings, go to the access tokens, and then you can create a write token, and then you can copy paste it here. Okay, and then we say push to hub, this data set will be pushed to the hub. So let me run the code. So it's doing all the processing and all. I will show you how the dataset would look like. It's a very small data set, so you can go to this settings, so it will show you the data set. So this is data set. So as you can see, here are the images of the person Ankush Chaudhary, and here are the labels which are generated by blip, and then I have modified where I have replaced a man or person with the Ankush Chaudhary, right? So this is the training data set we have created. There are about just 24 such images and associated labels. That's all the data set is. Okay, and then now we'll start the fine tuning of our model. We are going to create some environment variable where we are going to specify what is our base model that we use, where is our data set, and what is the fine tuning technique we are going to use, and where we are going to copy the model locally, and also where we're going to upload the model also to the Hugging Face, right? So we will just generate this some environment variables. Then we also need to log into the Hugging Face because we need to basically upload our model. So what we need to do is we need to grab the access token. For example, I can go here, go to the settings, go to the access token, invalidate, and I can refresh. I can copy this, I can copy paste this here so that it will use this model. So I've logged into the Hugging Face. Then I use an accelerate library from Hugging Face to fine tune my model. This is a very useful library that basically abstracts a lot of things needed to basically do a fine tuning of a model, and we can just focus on the application logic, right? So basically it has a really compatibility with the PyTorch. It does automatic gradient accumulation, mixed precision training, gradient clipping, the resource management, like doing the training in a distributed fashion. It all takes care of that. We don't have to worry about it. We can just focus on the actual logic of our application, right? So the code that I'm just going to use accelerate and configure a bunch of parameters. One parameter is the script that I use for training, finding the model using LoRa, and we will go through that. But bunch of parameters that it requires: what is the model name, which is the base name, data set we have created, then number of workers, resolution of the image. There are a bunch of different parameters that you can use to update, to specify the parameters for the model, right? How much you want to checkpoint, what is the validation prompt that you want to use for testing. You can specify all of that. And in my blog I have specified what is the function of each parameter, and you can go through this if you need to. But this is what it does. And as I said, it uses this script called train text to image LoRa.py, which actually is the script which takes this parameter and actually fine tunes the model, right? So basically the script is pretty straightforward. The diffusion model pre-training steps. Only the difference is since we are going to train only the LoRa, which is the low rank adaptation model, we are going to say, hey, just use a low rank model, which is the default value is about 8. And how do you initialize the LoRa weights to Gaussian models? And since we are going to train only the LoRa models, we are going to tell our unit model inside a diffusion model to say that only to use LoRa model and nothing else. And in the optimizer, we are going to just load the LoRa layer, so that this entire fine tuning just happens for only the LoRa layers. It's not going to update the entire weights of the entire diffusion model, right? It's just going to upload update the LoRa weights, which is like 2 low rank matrices that's going to generate with which we are going to update the model later on. But right now we're just going to train the LoRa models. And these LoRa models are basically nothing but it's an adapter layer that is formed and which is kept separate from the original layers, right? As I described in the diagram earlier over here. I'll go back again there. Here, right? So it's going to generate these two models and keep it as separate weights. That is what this code is doing. So once I run this code, it's going to run this code about 6 to 7 hours, okay? And at the end of this code, it's going to upload the model to basically Hugging Face again, and I will show you how that model looks like. So I've already done that once. Let me click on my profile. So this is the model that I have created, okay, and here here it creates queries, checkpoints and all, and uploads the model here. So once the model is, it takes about 5 to 6 hours, so you need to be patient while doing this. And once we find in the model, then we can use this model and use the same prompts as earlier to see how the model is behaving now. Okay, the model is uploaded to the Hugging Face now. So let's do inference again. So what we are going to do now is we are going to say, hey, now we have fine-tuned our fine-tuned models here, and we are also going to use the base model, which is the runways stable diffusion model. So we are going to do that, and again we are going to use the diffuser library. And now we are saying from pre-trained model, of course, load the base model, right? And then use the usual scheduler, the noise scheduler that diffusion model uses. And we are going to say now the attention model inside the unit. You use this the new fine-tuned model that we have created, right? That model is used to use the updates of the attention layers inside the unit models, right? And that's the only so we are just going to update those weights with this particular model. So you see how it's additive it is, right? If you don't use this, it's going to use the same behavior as the traditional diffusion model, but we are customizing it for Ankush Chowdhury use case. And these are the weights for that particular model, right? So we are going to convert this again model to GPU so it can run on GPU, and we will give the same about similar prompts, and then we will see how those images looks like once we do this, right? So let's run this and let's see what difference it produces this time. So it's downloading the model for the first time from that we have fine-tuned, and now we'll start generating the images. So as you can see, it really need to understand, it's so close to what we really wanted to do, right? So you see this particular example, right? And I keep fine-tuning the models. In one of the versions of the model I saw, I'll show you what I observed. So I got this particular result, right, which is pretty close. So you can fine-tune the model just by adjusting the weights of the model, but it's pretty close to the real photos of the Ankush Chaudhary, right? And you can fine-tune this hyperparameter of the model to get a better quality images, and I have done that a lot, and that's where I could get this particular quality. So I've adjusted these parameters which are here, which we use for fine-tuning, right, that I have showed you. Let me show it to you again. The one that we pass into the accelerate directory, accelerate tool. So a bunch of these parameters you can optimize. You try changing learning rate, max training steps, then the mix precision, and then you will at some point you will start getting a better quality images. So that's how basically we use the model to understand. See the same prompts we passed right now. Ankush Chaudhary wearing a suit, gangster, anime style, dancing. Now it really understand who the Ankush Chaudhary is, and he generates the image of this particular person only. So the images that we supplied to the model during the training was where this, right? I showed you that training model that we passed, right? So let me go back and show you again. So this was the training data that we passed. right? So you can see this was Ankush Chaudhary. So it just gathered this image of this particular person, and now you can generate a different type of images using any prompt, but really understands who this person is, and really give you the images of that quality. So this is how the LoRa can be used, and as you saw, the inference was very fast. Training also was just few hours. Without LoRa, the training can go for hours, and it will also cost you a significant money. So it saves you cost. At the same time, it gives you a very decent quality as it starts understanding the new concept. So here the example was for a person, but any enterprise company could also use the product like a soap or a phone or cloth merchandise, the jackets. Like a lot of different companies have tried adopting, fine tuning the diffusion models for their own products, and then giving that model out to their employees to generate new images which follows their brand guidelines, right? So that's the usefulness of LoRa model. Thanks and goodbye.